Hello, good evening everyone. This video is about Inertial Measurement Unit, and this is from Avalanche Breakdown YouTube channel. So in this document we will basically cover about IMU. IMU stands for Inertial Measurement Unit, and what we will see in this document is like these are the table of contents. Basic concepts are like what is an IMU, definition of an IMU, basic components of an IMU, 6-axis IMU, 9-axis IMU, what does an IMU actually measure, IMU output. Then we'll see an example, IMU on an autonomous vehicle. Then we'll see IMU on an autonomous vehicle. Then we'll see where are IMU used, why an IMU alone is not enough, why are IMUs important, industry use case, comparison of popular IMUs. Then we'll see some advanced concepts. What is sensor fusion? Why is sensor fusion necessary? Benefits of sensor fusion. Types of sensor fusion in autonomous vehicles. Dead reckoning. IMU interfaces. IMU data processing. Noise analysis. Uses of IMU in autonomous vehicle. And then we'll see a summary. Right. So this is what the table of contents is. I think there is a small mistake here. I will just check in the document how it is. Now let's go ahead. Now before seeing this document, right, one thing which is very important is like we know the key terms. We'll talk about IMU. IMU stands for Inertial Measurement Unit. Then there is something called as linear acceleration, magnetic field, inertia, accelerometer, gyroscope, magnetometer, autonomous vehicles, drones, roll, pitch, yaw, lidar, camera, radar, sensor fusion, dead reckoning, and SLAM. SLAM stands for simultaneous localization and mapping. So yeah, so these are all the things that we will see in this document. So yeah, let's go ahead. Now let's start. So we'll now see basic concepts. What is an IMU? An inertial measurement unit, IMU, is an electronic sensor system that measures the motion and orientation of an object without relying on external references such as GPS, cameras, and landmarks. Okay, an IMU continuously measures the physical quantity that describes how an object is moving. So what actually an IMU gives? It gives linear acceleration, angular velocity, and magnetic field. Okay, this is magnetic. This magnetic field is optional. In case you have a magnetometer inside your IMU. Using these measurements, an IMU can estimate what? Vehicle orientation, roll, pitch, yaw, direction of movement, in which direction it is going, velocity, position, and motion dynamics. An IMU is called an inertial sensor because it measures the effects of inertia, the tendency of an object to resist changes in its state of motion. Now next, what is definition? An inertial measurement unit, IMU, is an electronic device that measures an object's linear acceleration, angular velocity in many cases, the surrounding magnetic field to estimate its motion, orientation, and dynamic behavior. Now what are basic components of an IMU? The basic components are, as we have already seen, accelerometer. What does it measure? It measures linear acceleration, and the unit is what? Meter per second square, or G. Gyroscope, angular velocity, radian per second. Magnetometer, optional, Earth's magnetic field, and it is microtesla. Now there are types. The 6-axis IMU contains 3-axis accelerometer or 3-axis gyroscope. Measures what does this do? Linear acceleration along XYZ and angular velocity in XYZ. What about 9-axis IMU? 3-axis accelerometers, 3-axis gyroscope, and 3-axis magnetometer. In addition to motion sensing, it provides an estimate of heading yaw relative to Earth's magnetic field. So this is what is 9-axis. 9-axis IMU. Now moving ahead, what does an IMU actually measure? An IMU does not directly measure position or velocity. Instead it measures what does it measure? Accelerometer measures specific force, which is the non-gravitational acceleration acting on the sensor. Because gravity also affects the sensor, stationary accelerometer still reports approximately 9.81 meter per second square. For example, a car accelerating forward, acceleration is plus 2 meter per second square. The IMU detects this acceleration. Now gyroscope. IMU also has gyroscope. What does it measure? Measures angular velocity. Example, vehicle turning left. Angular velocity, yaw rate is equal to 0.4 radian per second. Right? So the gyroscope reports this rotational speed. Next, magnetometer measures Earth's magnetic field. This helps determine compass heading. Example, this is the vehicle is moving in this direction and the north is in this direction. The magnetometer determines the vehicle's orientation relative to magnetic north. That is what it does. Now IMU output. How does an IMU output actually look like? If you see an IMU, a ROS2 message, sensor messages IMU typically contains linear acceleration like x, y, z, angular velocity, gx, gy, gz, and orientation optional. In case it is a 9-axis, then quaternion, then qx, qy, qz, qw. Correct, right? So this is optional. Now, some IMUs provide only raw acceleration and angular velocity, while others include onboard sensor fusion to estimate orientation. This is important. Now, example, IMU on an autonomous vehicle, right? Imagine an autonomous car waiting at a traffic signal. Then what are the different, what will be the outputs of different sensors? Vehicle is stationary, accelerometer x is equal to 0, y is equal to 0, z is equal to 9.81, right? Gyroscope x is equal to 0, y is equal to z 0 equal to 0. The IMU detects the vehicle is not moving but experiencing gravity, right? This is what it shows. Now vehicle accelerates forward. Now x is equal to plus 3 meter per second square, y is equal to 0, z is equal to 9.81. The IMU detects forward acceleration. Now what happens when the vehicle turns left? Gyroscope, yaw rate 0.5 radians per second. The IMU detects the rotational motion. So this is what will be the output when the car is moving. Okay. So vehicle drivers over a speed bump, accelerometer, vertical acceleration spikes. The IMU senses sudden vertical movement. Correct, right? So this is, I think this is well understood. Where are IMUs actually used? IMUs are found in a wide range of systems: autonomous vehicle, mobile robots, drones, aircraft and spacecraft, smartphones and tablets, wearable devices, industrial robot, marine navigation system, virtual and augmented reality headset, construction and agricultural machinery. Why an IMU is not enough? Why an IMU alone is not enough? Although an IMU provides fast and continuous motion measurements, it has an important limitation. Small sensor errors accumulate over time. This is very important. Very important line. For example, a tiny gyroscope bias can cause orientation estimates to drift. Small acceleration errors integrate into large velocity errors. Double integration of acceleration causes position estimates to drift rapidly. This is actually very important, and and I think people should keep this in mind, that IMU is not only using IMU is not enough actually. As a result, autonomous systems combine IMU data with other sensors such as GNSS, GPS, LiDAR, cameras, wheel encoders, radar. This process is called as sensor fusion, enabling accurate and reliable localization. So what this is basically saying is, like, IMU data, it accumulates error over a period of time. So what we can do is, like, we can sensor fuse. We can fuse the IMU data with data from other sensors, so that error can be decreased, right? So this is why an IMU alone is not enough. Why an IMU is important? An IMU is one of the most critical sensors in modern navigation and control systems because it provides continuous high frequency measurement of motion even when external sensors are unavailable or unreliable. Unlike GPS or camera, which depend on external signals or environmental features, an IMU is self-contained. It measures the vehicle's motion directly, allowing the system to estimate orientation and movement in real time, right? Continuous motion measurement. An IMUs typically operate at frequencies of 10 to 1000 Hz or higher, providing updates every few milliseconds. This high update rate is essential for fast control loops in autonomous systems. So if you have ever worked with IMUs, you will see that if you start taking IMU data, and in an instant, maybe after 2 seconds, if you just stop taking IMU data, you will still see a lot of data. So that is what it is, that it has very high frequency. This is what this thing means. Next, works without external infrastructure. An IMU does not require GPS, satellite, camera, visible landmark, road marking, wireless communication. This makes it indispensable in environments where external references are unavailable, such as tunnels, underground parking garages, dense urban areas, forests, underwater or in space. Essential for vehicle stability and control. Vehicle controllers rely on IMU measurements to estimate roll angle, pitch angle, yaw rate, linear acceleration. These measurements support functions such as electronic stability control, autonomous steering, traction control, motion planning, and vehicle state estimation. All these examples are related to autonomous driving, but IMU as a sensor is not only used in autonomous driving, but it is a very popular sensor which is used in many fields, as we have already discussed earlier. Improves localization through sensor fusion. Because IMUs provide accurate short-term motion information but drift over time, they are combined with slower, globally referenced sensors such as GPS, LiDAR or cameras. This combination allows the system to maintain accurate localization even when one sensor becomes unreliable. So as we have already discussed, what we actually do is, like, we use not only IMU data, but we fuse it with the data of other sensors, enabling operation in GPS denied environments. Autonomous system often encounter situation where GPS is degraded or unavailable. In these cases, the IMU continues to estimate motion, bridging the gap until reliable external measurement become available once again. Suppose if you are in a tunnel, then what happens is you won't have very good GPS signal. Then what you can do, and at that point of time you can rely on IMU data to go from point A to point B, and once after reaching point B, suppose you get the GPS data back, so that is a very reliable. You can correct the error and then move ahead. So industry use cases, the importance of IMUs extend beyond autonomous vehicles. Automotive navigation, advanced driver assistance system, autonomous driving, stability control in robotics, mobile robot, robotic arms, warehouse automation, humanoid robots, aerospace, aircraft, altitude estimation, missile guidance, spacecraft navigation, marine. This is altitude. This is wrong. Marine ship stabilization, underwater vehicle navigation, consumer electronics, smartphone screen rotation, fitness tracking, game controllers, healthcare, motion analysis, rehabilitation devices, wearable health monitor. So these are like comparison of popular IMUs. You have like Bosch, Microstrain, Xsense, VectorNav, ADIS. These are all different companies which produce IMUs. So you can see, what type of sensors these are, what is the accuracy, what is the cost, and what are the applications, right? So with this we have covered half of the document, wherein as we discussed at the beginning, so like this document is divided into two parts, wherein first part is the basic concept and the next part is advanced concept. So we have completed this basic concepts. Now we will move towards advanced concepts. So yeah, let's move ahead. Now the first thing is like, what is sensor fusion? Sensor fusion is a process of combining data from multiple sensors to obtain a more accurate, reliable and robust estimate of the environment and the vehicle state than could be achieved using a single sensor alone. Each sensor has its own strengths and weaknesses. By intelligently combining their measurements, autonomous system can compensate for individual sensor limitation and improve overall performance. For example, an IMU provides high frequency motion information but drifts over time. This we have already seen. A GNSS receiver provides globally reference position but suffers from low update rates and signal outages. By fusing both the sensors, a system can achieve accurate and continuous localization. This is very important. Next, what is definition? A sensor fusion is mathematical process of integrating measurements from multiple sensors to estimate the state of a system with greater accuracy, robustness and reliability than any individual sensor can provide. Why is sensor fusion necessary? See, why? Because no sensor is perfect. Each sensor technology has inherent limitation that can affect its accuracy, reliability or availability depending on environmental conditions. So basically what we are actually trying to say is like, we need to have a system that is accurate most of the times. That is most of the times in the sense in 99.999% of the times. Since each sensor has its own limitations, so what we actually do is we try to integrate different sensors, and once we have different sensors and they all work together, then you can get a very accurate data, and with that accurate data you can do accurate control of the vehicle. So that is what it is all about. So what is IMU? Strength is very fast motion measurement. What is limitation? Drift accumulates over time. Then GNSS, GPS is global position, signal loss, multipath, low update rate. LiDAR, high accurate 3D mapping, cannot measure vehicle dynamics directly. Camera, rich visual information. Next, sensitive to lightning and weather. Wheel encoder, accurate short-term distance, wheel slips causes error. Radar, reliable object detection in adverse weather, limited spatial resolution. So these are the things. If an autonomous vehicle relied on only one of these sensors, its performance would degrade significantly in many real-time scenarios. That's why when you see an autonomous vehicle, you see many sensors on top of it. Sensor fusion allows the system to combine complementary information and produce a more accurate estimate of vehicle position, orientation, velocity, acceleration, environment, object location. So the goal is to have a very accurate information. And how is it that we will be able to get an accurate information? Is when we have multiple sensors. What do we do when we have multiple sensors? We try to fuse all of them so that we get very accurate data from them. So that is what it is all about. Next, what is benefits of sensor fusion? Sensor fusion provides several important advantages like improved localization accuracy, increased robustness, reduced sensor noise, compensation for sensor failures, high reliability, better obstacle detection, continuous operation during temporary sensor outages, improved vehicle safety, better performance under challenging environmental conditions. Now example, consider a self-driving car entering a tunnel. Before entering, GPS is okay, LiDAR is okay, camera is okay, IMU is okay. Inside the tunnel, GPS is lost, camera is limited, LiDAR works, IMU works. Now the story is, although the GPS becomes unavailable, the IMU continues measuring the vehicle's motion, while LiDAR maintains localization by matching the current scan against a previously built map. Together they allow the vehicle to continue navigating safely through the signals return. So here we, in this example, what we see is like before entering the tunnel all the sensors were working, but when we entered the tunnel some sensors were not performing as they should have been. As a result of which, since some sensors were not working, there were others which were working. So inside the tunnel, IMU and LiDAR were working very well. So as a result of which, we were able to navigate from start of the tunnel till end of the tunnel without any issue. Right. Next, types of sensor fusion in autonomous vehicle. Modern autonomous driving system commonly use the following sensor combination: IMU GNSS, IMU LiDAR, IMU camera, IMU wheel encoder, IMU radar, LiDAR camera, camera radar, multi-sensor fusion, all available sensors. The following section describes the role of IMU when fused with other sensors. Here basically we will see, since this document is about IMU, we'll focus more about IMU. Okay. Then IMU plus GPS or GNSS. Why combine them? An IMU provides accurate short-term motion estimate but gradually accumulates drift. GPS, or more generally GNSS, provides an absolute position reference but updates relatively slowly and may experience outages or multi-path errors. By combining both, the system benefits from the strength of each sensor. IMU strength, high update rate, 100 to 1000, measures acceleration and angular velocity, operates in tunnels, under bridges, no dependence on satellite. IMU weaknesses: position drift over time, orientation drift due to gyroscope bias. GPS, absolute global position, no cumulative drift. GPS weakness, low update rate, right? Typically 1 to 10 Hz. Signal blockage in urban canyons, tunnels, or under dense foliage. Fusion concept. The IMU predicts the vehicle's motion continuously between GNSS updates. When a new GNSS measurement arrives, the localization algorithm corrects the accumulated drift. This is what we even discussed earlier, right? IMU is like motion prediction, GNSS is position correction. This is what happens. Accurate localization. This is commonly implemented using an extended Kalman filter or other state estimation techniques. Next, applications: autonomous vehicles, aircraft navigation, drones, marine navigation, mobile robots. So this is all about this. Right? Now IMU plus LiDAR, when do we use it? Why combine them? LiDAR generally generates high accurate 3D point cloud but does not directly measure the vehicle's motion. During rapid movement, scans become distorted. Right? IMU provide high rate rotational and linear motion information that helps compensate for this distortion and improves localization. Now IMU contribution: motion prediction, orientation estimation, scan de-skewing, high frequency updates, improved initialization. LiDAR, accurate map matching, environmental geometry, loop closure support. Drift correction. So what happens? You have a LiDAR scan, then motion compensation using IMU, then feature extraction, map matching, and localization. So what is it that we are actually trying to tell is like LiDAR can give very good, very accurate 3D point cloud, but the LiDAR in itself cannot measure the vehicle's motion. This how will we do? This we will do with the help of IMU, because we have accelerometer. It will calculate acceleration, right? So this is all about it. And next, IMU plus camera. Why combine them? Cameras provide rich visual information but struggle with rapid motion, motion blur, poor lighting, and textureless environments. An IMU supplies continuous motion information that stabilizes visual tracking and enables accurate pose estimation. Camera contribution: feature detection, lane detection, object recognition, traffic sign recognition, semantic understanding. IMU contribution: orientation estimation, motion prediction, high rate rotational information, short term pose estimation. Right? This is what it is. How do you fuse them? You have camera images, then you have IMU motion, then you have visual inertial odometry, and then you have pose estimation. I hope this is understood. So basically what you are trying to do is, through camera you are seeing different features which are present, and you have an IMU and it helps in motion, and when you combine both of them you get, like, visual inertial odometry, and as a result of which you get to know where you are. Pose estimate, you can do pose estimation. So this is what was about that. Next, let us see IMU plus wheel encoder. Here there is an I, but for some reason we are not able to see it. Why combine them? Wheel encoders measure wheel rotation and estimate vehicle speed and travel distance. However, they are susceptible to errors caused by wheel slip, skidding, and uneven terrain. IMU complements wheel encoders by measuring accurate vehicle acceleration and rotation. So yeah, so basically when we have two sensors, right, the positives of some sensors will have positive things in one situation, and other sensors will have positive points in another situation. So like it is better to use both of them, so that you always have good points. So that is what it is all about. Wheel encoder contributions like wheel speed, vehicle speed, distance traveled, odometry. IMU contribution, yaw rate, pitch angle, roll angle, acceleration. How do you use them? Wheel speed, and then IMU, then vehicle state estimation you get to know, and then odometry. Next, now we have come to IMU plus radar. Why combine them? A radar performs well in rain, fog, snow, thus providing robust measurements of object range and relative velocity. However, radar does not directly estimate the vehicle's orientation or motion. The IMU supplies this missing motion information. It is very important to understand that IMU has three sensors: accelerometer, gyroscope, and magnetometer. With these three sensors, whatever information you can get, you are always providing it to other sensors. That's all. That's what it is all about. Radar contribution is like object distance, relative velocity, obstacle detection, collision bonding. IMU contribution, vehicle motion estimation, orientation, rotation compensation. Fusion process, radar, and then IMU, you do object tracking, and then dynamic object estimation. Now I think we have already seen this, right? IMU plus GNSS. Although the term GPS and GNSS are often used interchangeably, they are not identical. GPS refers specifically to the United States Global Positioning System. GNSS is Global Navigation Satellite System, is a broader term encompassing all satellite navigation constellation including GPS, GLONASS, Galileo, Baidu, QZSS Japan, and Navig India. Like modern autonomous vehicles typically use multi-constellation GNSS receiver rather than GPS alone because they can track more satellites and improve positioning and accuracy and availability. The principle of IMU plus GNSS fusion are the same as IMU plus GPS fusion. IMU provides continuous high frequency estimation of motion. The GNSS receiver provides globally reference position and velocity updates. A state estimator such as extended Kalman filter combine these two measurements to produce a smooth, accurate and robust estimate of vehicle's state even during brief GNSS output. So you have two sensors, and the output of these two sensors are generally given to an extended Kalman filtering, and with the help of this extended Kalman filtering you get to know the you get to know vehicle's state, right? Next states you can find out. So this combination is a cornerstone of modern localization system used in autonomous vehicle, drones and robotics. So this is how you basically try to localize it, right? You have GNSS system, you have IMU. What do? You can find you can localize it very well. Okay, so that is what it is all about. So yeah, so sensor fusion pair IMU plus GNSS GPS. What is IMU? High rate motion prediction and orientation. Other sensors, absolute global position and velocity. Then main application, vehicle localization, UAV navigation, robotics. Right, then IMU plus LiDAR, motion. What is IMU? Motion compensation, orientation, scan deskewing. This 3D mapping and precise localization. What are the main application? Autonomous driving and SLAM. IMU plus camera, motion prediction and attitude. It is not attitude. This is like altitude estimation. This other sensor, visual features and semantic information. What about this? See, visual inertial odometry, VIO or AR/VR drones. IMU plus wheel encoder, rotation, accelerometer, altitude, wheel speed and travel distance. This is vehicle odometry, mobile robots. And next, last, IMU plus radar, vehicle motion and orientation. Next, object range and relative velocity. So whatever see, one thing that you have understood is like this helps to find this IMU, right? The IMU helps to find next state, right? It has three things: accelerometer, magnetometer and gyroscope. And accelerometer will give you acceleration. So with that you can find different parameters. If you integrate acceleration. So yeah, so this is what it does. It actually predicts motion, right? So yeah, so let us move ahead. So in practice, modern autonomous vehicles rarely rely on a single fusion pair. Instead, they integrate data with GNSS, LiDAR, cameras, wheel encoders, radar and high definition maps simultaneously through a centralized state estimation framework, allowing the vehicle to maintain accurate localization and situational awareness across a wide range of operating conditions. This is very important paragraph, right? So with this we have actually come to an end of the sensor fusion. Now we will talk about something called as dead reckoning. What is dead reckoning? Dead reckoning, DR, is a navigation technique used to estimate the current position of a moving object by starting from an unknown initial position and continuously integrating measurements of speed, direction and elapsed time. Unlike GPS based navigation, dead reckoning does not require external references. It relies entirely on onboard sensors such as IMU and wheel encoders. Principle of dead reckoning. The basic idea is start from a known position, measure how far the wheel has moved, measure the direction of the movement, complete the position estimate. Mathematically, velocity is obtained by integrating acceleration, position is obtained by integrating velocity, orientation is obtained by integrating angular velocity. Okay, so this is what it is, and this is very important. Now, since every integration introduces small errors, these errors accumulate over time, causing drift. Okay, I hope this is very well understood. And yeah, so once again, what is dead reckoning? Dead reckoning, so instead of studying this, maybe you can do start from a known position, measure how far the vehicle has moved, measure the direction of movement and update the position estimate. And that is, dead reckoning is a navigation technique used to estimate the current position of a moving object by starting from a known initial position and continuously integrating measurements of speed, direction and elapsed time. So what are IMU interfaces? What are different I2C, SPI, UART, USB, CAN-FT and Ethernet? Okay. So yeah, so you have different speed, cost, resistance, typical application. You can have a look here. Thanks. IMU data processing. Raw IMU measurement cannot be used directly for localization or control. They must be first processed to improve accuracy and remove unwanted effects. So you have raw data. You get data from the accelerometer. You get data from gyroscope, right? And then you will have timestamps as well. So what do? There is something called as timestamp synchronization. Every IMU measurement must have an accurate timestamp. Incorrect timestamps lead to localization errors, sensor misalignment and poor fusion performance. Then you have to calibrate the sensor as well. Why is calibration required? Calibration corrects bias, scale factor, axis misalignment, temperature effects. Next, coordinate transformation. Convert measurements from IMU frame to vehicle frame using static transform. Next, filtering. So in the process of removing noise from the IMU data, you have many filters, right? Filters. The typical filters are like low pass filter, remove high frequency vibration used for accelerometer gyroscope. You have high pass filter, removes slow drift. You have moving average filter, smooths noisy signal. Median filter removes isolated spike. Butterworth filter provides smooth filtering with minimal signal distortion. You have orientation estimation. You have roll pitch here. You estimate roll pitch here using complementary filter, Kalman filter, Madvick filter and Mahoney filter. Now you do sensor fusion. We have already seen you do sensor fusion using what? Extended Kalman filtering, using combined IMU with GNSS LiDAR, camera, radar, wheel encoder. Now what is the final output? Processed IMU data is used for localization, vehicle control, motion planning, SLAM. SLAM stands for simultaneous localization and path tracking. Next, noise analysis. Every IMU measurement contains some levels of uncertainty or error, commonly referred to as noise. Understanding these noise characteristics is essential for designing filters and estimating sensor reliability. So, first of all, what is noise? Noise is a random fluctuation of superimposed on the true sensor measurement. For example, an accelerometer lying perfectly still would ideally measure 009.1, but in reality it may produce something like this: 0.02 minus 0.09.79. These variations are caused by sensor noise. And I hope you would have definitely, if you have ever worked with an IMU sensor, you would have definitely seen these measurements. Uses of IMU in autonomous vehicles, right? Now this is very important since we are basically talking about autonomous vehicles. So now we will think in perspective of autonomous vehicles. The IMU is one of the most important sensors in autonomous vehicle because it continuously measures the vehicle's motion and orientation, providing essential information for perception, localization, planning and control. Localization answers the question, where is the vehicle? The IMU contributes by providing high rate orientation updates, motion prediction between GNSS and LiDAR updates, short-term pose estimation. It is fused with GNSS, LiDAR, camera and HD maps to achieve accurate localization. State estimation. State estimation determines the complete dynamic state of a vehicle, including position, velocity, orientation, angular velocity, linear acceleration. So what basically you do is, like, suppose you have data from IMU and GNSS, and then you feed it to Kalman filtering. Then, as we saw earlier, like suppose we go inside a tunnel and we lose GNSS data. So with the help of IMU data, since with the help of IMU data, we know we have data from accelerometer and gyroscope, so we can estimate how the next states of the IMU will be, right? So with that we can estimate the position after some time. The IMU supplies the high frequency inertial measurement that allows state estimation such as EKFs, extended Kalman filters, to produce smooth continuous estimates. Next, vehicle dynamics. The IMU measures the physical motion of the vehicle such as longitudinal acceleration, lateral acceleration, vertical acceleration, roll, pitch, yaw, right? These measurements are crucial for stability control, suspension analysis and vehicle modeling. Now motion prediction. Between updates from slower sensors like GNSS or LiDAR, the IMU predicts how the vehicle is moving. This prediction step is fundamental in recursive state estimation algorithms and then allows the system to maintain continuous localization. Lane keeping. Lane keeping system use the IMU to monitor vehicle altitude and yaw rate. By combining IMU data with camera-based lane detection and steering measurement, the controller can determine whether the vehicle is drifting from the lane and compute corrective steering commands. SLAM. SLAM stands for simultaneous localization and mapping. SLAM enables a vehicle to build a map while simultaneously determining its position within that map. The IMU improves SLAM by providing an initial motion estimate, compensating for rapid rotation, de-skewing LiDAR scans during movement, improving visual feature tracking, increasing robustness during fast maneuvers. Examples include LeoSLAM, Fast Leo, WINS Fusion, or VSLAM 3, all of which tightly integrate IMU data with LiDAR or camera measurements. Now, emergency control. During emergency maneuvers such as sudden braking or obstacle avoidance, the IMU provides real-time measurements of rapid deceleration, sharp yaw rotations, and vehicle roll and pitch. These measurements enable systems such as electronic stability control, autonomous emergency braking, rollover prevention, traction control. By supplying high frequency motion data, the IMU allows controllers to react within milliseconds, improving the vehicle stability and passenger safety. So yeah, so with this we have come to the end of this document. So what is it that we have studied so far? The summary is the IMU is a foundational sensor for any system that needs to understand how it is moving. It delivers fast continuous movement of acceleration and rotation, enabling real-time control and navigation, while it cannot provide accurate long-term position estimate by itself. Due to its drift, its integration with GPS, LiDAR, cameras and other sensors through sensor fusion makes it indispensable in modern autonomous systems. For this reason, the IMU is often considered the motion backbone of robotics, aerospace and autonomous driving technologies. So with this we have come to the end of this document. So in this document I will just go to the top once again. So we have covered inertial measurement unit, and these are all the things that we have seen. We have covered basic concepts of what is an IMU, definition of an IMU, basic components of an IMU, 6-axis IMU, 9-axis IMU. What does an IMU actually measure? IMU output is then example IMU on an autonomous vehicle. Where are IMUs used? Why an IMU alone is not enough? Why are IMUs important? Industry use case, comparison of popular IMUs. Now we have advanced concepts like what is sensor fusion, why is sensor fusion necessary, benefits of sensor fusion, types of sensor fusion in autonomous vehicle, dead reckoning, IMU interfaces, IMU data processing, noise analysis, uses of IMU in autonomous vehicle, and summary. So yeah, so I think with this we have come to the end of the document. Thank you very much.